Okay, maybe we get started. Yeah, okay. All right, well, welcome. I'm glad we're all here on time. I'm impressed with the third day. So this morning we're going to talk about parallelization of geospatial workflows in CrashJS and Python. But before we dive in, let me figure out how to switch slides. Yeah, my name is Caitlin, and I'm a fourth-year PhD student at North Carolina State University, where I'm in the Geo for All lab there, and one of my committee members and lab mates is Anna Petrasheva, who is a true GRASS royalty. She's been contributing to GRASS for over 10 years and is an expert in parallelization with GRASS and has parallelized some of the GRASS modules herself and mentored others in doing so. She's also on the CrashJS project steering committee. So I'm very honored to work with her, and yeah, she wishes she could be here. And I've also, since working with her, started to contribute to GRASS, specifically around integrating CrashJS with Jupyter notebooks. So today, right now, we'll just talk about some key concepts and vocabulary in parallel computing, just so we're all on the same page, if you know what we're talking about. And then we'll go through some pretty simple and practical approaches to parallelizing geospatial workflows. And along the way, we'll also get to know how to use CrashJS in Jupyter notebooks. Okay, so first, I'll talk for a little bit. Bear with me, probably 15 minutes. And then the rest of the time, we'll work through two notebooks that are in the GitHub repository. The first one is sort of more of an introduction to the different methods and more general. And then we'll look at a specific case study looking at urban growth modeling using the futures model. And we'll compute a large section of the state of North Carolina, which will be exciting. Okay. All right, so first, the me talking part. Yeah, so if you've ever sat at your computer and waited for your code to run, you might be doing things using serial computing, which is when you're performing computations one at a time, one after the other. And an alternative to that would be to use parallel computing, where you're doing multiple computations at the same time. And so parallel computing takes advantage of multiple cores and threads. So if you have a laptop, you might have something like 8 cores. If you're using a desktop or a server, you probably have like tens of cores CPUs. And if you're using an HPC, then you can access thousands of cores. So now is a good moment to think about how many cores you might have on your machine. If anyone wants to check and shout out how many they have, they're welcome to. You might not have 8, you might have 16, you might have less. You can use the LS CPU or nproc if you're using Linux. And if you would prefer to do it with a menu, you can also find it under like the task manager of Windows and the Apple menu on Apple machines. HTOP works, nproc, NPROC, or LS CPU. What? 8. Nice. Yeah, that's how many I have. Always good to know. You don't want to use all your CPU. Okay, but so just because your computer has 8 cores doesn't mean that when you run a program, it's going to use all of those cores. Programs have to be told to run on multiple cores. So yeah, just because you have a powerful computer doesn't mean you're using all of your computational resources. You have to tell it to do so. And then even if your program is using 8 cores, that doesn't mean that it's going to be 8 times faster. And this is because even parallelized processes have some serial component to them. And that could be like the startup and shutdown procedures. It could be like, patching the results together at the end, or the initial dividing of the process, and then the parallel overhead. So the splitting of all the different tasks, and then the management of the queue and passing the tasks out to all the different cores and collecting them back. That takes computing power. So when you parallelize a program, the speed won't increase linearly with cores. Like it's tempting to think that if you double the amount of computational resources, your program will double in speed. But as you can see here, this little diagram is showing that the sequential portion always remains the same, even as you increase the number of cores. So the parallel portion gets faster and faster and faster, but because that sequential portion stays the same,
it's more time needed to collect. And then
yeah,
sequential portion could be bigger.
yeah, even bigger. Thank you. Okay, and this is actually Amdahl's law that says that as you speed up the parallel portions, the serial portion will always limit how fast your program can go. Okay, and so we might want to measure then how much we've improved our performance by increasing the number of cores. And so the first way we can do that is with parallel speedup. So speedup is the ratio of the serial compute time to the parallel compute time. So here's a little thought question. If it takes a process 1 minute to run on one CPU and 30 seconds to run on 4, what's the speed up? Yeah, nice. Okay, and then another way of measuring it is to divide the speed up by the number of cores. So yeah, so that's the speed up divided by the number of cores. So then you're getting parallel efficiency. It'd be cool. Okay, so then here's the same question. If it takes 1 minute to run once on one CPU and 30 seconds to run on 4 CPUs, what's the efficiency? Yeah, so 50%, which is pretty low actually in the grand scheme of things. It means that you're using only about like 50% of the computing power that you've requested. And that's context dependent too. Like maybe that's fine if it's just on your local computer and it's really worth that you save those 30 seconds because you're going to do the task over and over again. But if you're running on an HPC, your manager might not be very pleased. It's also data and parameter specific. So if you were to change the, say like the extent of your rasters that you're processing, so you're going to process it over a larger region, or you change some of the parameters in your model or program, then it will also change the efficiency. Okay. So here's an example of how we can use parallel efficiency to do what's called benchmarking. And this is an example of a moving window analysis in Grass called r.neighbors, and it's smoothing a DEM. And we're using different window sizes, so 7 by 7 cells, so quite a small window, and then 31 cells is a big window. So we're changing a parameter of the model, and then we're running each of those windows over the same extent with an increasing number of cores. And so you can see that as we increase the number of cores, on all 3 different window sizes, the computation time drops, but they have really different parallel efficiencies. So this could be really important if you're using a cloud computing environment and you know that you want to have an efficiency above 50%, you might want to do some benchmarking to see, okay, if I'm running with a 31 cell window, I really do want all 16 cores, that makes sense for me. But if you're only using the 7 by 7 window, then you're not really gaining anything by using all 16 cores. You're actually sort of optimized back at 2 cores, maybe is the 60% efficiency that you want. This is also useful if you have to pay for your computational resources. You can look at this and kind of optimize your cost benefit analysis. Okay, so all these examples so far are examples of strong scaling, which is where we're keeping the size of the problem the same, but we're increasing the number of cores. And that's governed by Amdahl's law, like we were talking about earlier. Another thing to consider is weak scaling, and that's when you're increasing the problem size as you increase the number of cores. So here's like a diagram. So we've been doing strong scaling where we're taking our single problem, our one raster, and we're dividing it among ever increasing CPU. Another problem that we might want to consider is what would happen if we wanted to do, we've tested it on a small region using one core, but we want to do it for the whole entire globe using a proportional number of cores to that. So the computation per CPU is staying the same, but the number of CPU and the problem size is increasing together.
This approach would be that, for example, one state in United States, we have to calculate the same for 4 states. So, and then for you have the same number of cores as many as states in the United States, then you do it this way, yes? So this is weak scaling.
Yeah.
Yes.
Well, it's important to like the performance. Amdahl's law determines like how a project will scale if you're using strong scaling. But if you wanted to say deploy your algorithm on like a global scale and you were going to use an HPC instead of your 8 cores on your laptop, then you'd have to consider how your project, like how the weak scaling goes, and that's important for like memory issues and it's much more relevant in like distributed computing. Yeah.
Well, memory is, for example, it's strong version, the more usage is more or less the same because you just segmentize the same data set into smaller pieces to put on different cores. In the week, you just multiply this data set among cores, so the limits. Memory limits is much more important in that case.
Yeah, you'll find different bottlenecks, in your code with weak scaling. And that's governed by Gustafson's law, which we won't play as much with today, but if you're considering using distributed computing, I would encourage you. Okay, and so approaches to how we can parallelize our workflows. There are 2 general strategies we might want to employ if we're staring at our serial code and wondering how we're going to make it faster. The first is a data parallelization approach. So we're going to take our data and we're going to chunk it up into different squares or regions by, state or region, and you might need overlap between them, but then we'll disperse those to all run the same code. The second would be a task-based approach. So if you have tasks that can run independently from each other, for example, this one's showing like, say you have 4 different cell phone towers and you want to know the view shed, or you want to know the cumulative view shed. Well, they're all independent tasks. The view shed of one doesn't affect the view shed of the other. So they can all be run in parallel at the same time, and then we could sum them together at the end. So that'd be a task-based approach. Okay, and that's all for the like vocabulary and key concepts of this so far, but there's so much more out there. We don't cover like GPUs today or OpenMP, distributed memory, which I was talking about earlier, like message passing interface, and how to submit HPC jobs, but the materials in this are like directly applicable to that. So this will get you started. And then we're only using Python, Bash, and Grass today, and there's so many other things out there for parallelization like Dask, Apache, Sedona, Hadoop, and more, but we won't get there today. Okay. All right. Then I was going to talk about Grass, why we're using Grass, Python, Bash, what we're going to do today. But does anyone have any questions on what we just talked about? What I just talked about? Yeah.
What is the diffusion?
Which one?
Like it's in the example set, calculating cumulative diffusion.
Oh yeah. Yep. So if you sum all the view sheds together and you want to know what points are, well, it's an intersection of all the view sheds. So like how what points are visible by all the points? What points are visible by just one viewpoint? Yeah. Yes. Yeah, so if you're summing them all together, it's what. Maybe the better, if you had people on a fire tower looking for fires, you might want to know what your coverage is. Yeah, or the cell phone tower example, where you're going to have cell phone reception would be a cumulative viewshed. Okay. Anything else? Okay. Okay, so today we're using CrashJS, which has been around for a little while. It's a desktop GIS, but it's also a pretty powerful geoprocessing engine. It has over 400 tools in the main library, and then an additional like over 400 tools available as add-ons. So it's like an extremely extensive library that's been developed for a long time, primarily in C. And because it's been developed by academia, there's also a lot of like, like citations and niche tools that are really useful in specific fields. And then finally, it has this like native data format that avoids projection mismatches and lets you like set the resolution and spatial extent that you want to run a computation over, and lets you do that without like clipping your data or resampling it. So it like has this native data format that it will index through. So it runs really fast once it has its data in its native data format. Okay, so it is a traditional desktop GIS, and as of like a year and a half ago, or like I think 8.0 was the preliminary release, version 8.0 of GRASS, it's a single window. So it feels like all the other GIS software that you might be familiar with. And it's also a geoprocessing engine. So it has an API for Python and R and C, and then there's a command line interface too. So very convenient if you're using those. And then finally, we're also using it because it has a lot of internally parallelized tools. So you just need to tell it how many cores you want your tool to use. And you'll make your work faster. Okay, and then we're going to use Python and Bash today, just because they do have convenient GRASS APIs, and they both have great parallelization libraries. And then we're going to run it in Jupyter Notebooks, which I was going to talk about, but we're all familiar with Jupyter Notebooks, which is great. Okay, and then in the second half, after the coffee break, we'll look at a case study, the second notebook, which is on modeling urban growth. And we're going to use the futures model, which was developed at NC State. And it's an urban growth model that's patch-based and stochastic. So every single time you run the model, the output will be slightly different. And it has positive feedback. So the output of the time series and like is if one patch of urban development starts, it's positive feedback, and it'll likely attract more development around it. Yeah. Okay, so its output is developed. It tells you which cells are likely to develop over the next, 50 to 100 years, however long you're forecasting. And so the output looks like this, where green cells are undeveloped, and then the shades of orange are the developed cells, and the number in them corresponds to the year at which it develops. So the 0 cells were developed at the start of the simulation, and then the 33 would be developed 33 years in the future, 27 was developed 27 years in the future, and you can tell it's kind of growing in patches. So yeah, it uses a patch growing algorithm.
Is it like based on the slopes or something or not?
It's
like,
yeah, it takes into consider a bunch of inputs. I guess I should have mentioned those, and I don't know that I can list them all on the top of my head, but land cover, historical land cover and current land cover, population projections, protected areas, like the desirability of the land, so it will like distance from roads, water bodies, from parks or protected areas. Yeah, I think it might take into consideration slope. I think there's some more,
But I mean, you have already calibration of those parameters in the predictions, right?
yes,
And what we're gonna see like mostly like the outputs.
yes. Well, we'll run through the whole. You have to create all these different predictors and then you run the simulation, and the actual workflow is quite complex. So today we're going to have the calibration of the model pre-computed for us, but there is a second notebook in the repository showing how to do the calibration and compute the development potential, which is the futures potential model right there. So today we'll just do futures demand, which is how much land demand there'll be in every year in the future. So it like projects takes historic development and population patterns and then projects it into the future. So as if the population is going to increase by 10,000, that will mean that we probably need, so many acres of land to house that population increase. So that's the demand. And then the calibration and potential will be run for us, and then we'll do the simulation. So we'll run the patch growing algorithm and I think we're going to do it 100 times. And then we'll take all those in together and make a development probability map. So we're going to do a lot of computation. Did that answer your question?
Yeah, thank you. Thank you.
Yeah. Okay. Any questions about that so far? Otherwise, we can get started in the notebooks. No? Okay. Okay. Yeah, so I'm gonna escape out of this. So if you haven't had the chance to download anything before this workshop, I recommend that you run it on the cloud. So you can use Google Colab or Wholetail. I like Wholetail. It has slightly more computational resources. And there are directions for it in the README of the GitHub. And I'm using Wholetail today. So maybe raise your hand if you're looking at a notebook. This is working for you. Okay. Yeah. Is anyone having problems? Yeah, loading. Yeah, it takes a minute to launch no matter where it is. Can people in the back read the screen? I can make it bigger too. A little bit, yeah. Did that make it bigger? Right. Yeah, okay. Cool. Okay. All right, then let's get started. Okay, so we're going to be using a lot of Bash and Python. And the first thing you need to know is that the cells are defaulting to Python, but if we use this little magic %% bash, then it will run the whole cell in bash. So we can switch between them if we want. And because we're going to start a graph session in the background, we can run tools either way, and it will modify the same graph data set. Yeah. Okay, so first step, we download our data. And then we start up Grass. So we just point it to where Grass's Python libraries are. It has that Python API I mentioned earlier. And then we're going to start a Grass session in the data set that we have. So that native Grass data format that I was talking about earlier. And it has an internal organization. So the Grass project is OpenGeoHub 2023. And inside of that, we have a couple different map sets. The permanent one, which has all the data that we're going to use, which right now, I think it just has the county outlined for the regions of North Carolina that we're going to study in the second half. And then a lot of land use rasters. but we're gonna start in the other map set, so we'll be able to access all those data sets, but we're currently in map set from part 1, so that's what we did up here. Okay, Yeah.
This is the one that throws a lot of people off.
yeah,
So why do you need 3 map sets and why one called permanent?
yeah, okay, great question, yeah. I was gonna like try and like skim over to get to the parallelization stuff, but I think we should pause here and talk about it. Okay, so every GRASS project is united by, or like defined by, its coordinate reference system. And so all of our data is living in this EPSG 3358 project, and it's like native GRASS format in a GRASS database. And then inside that project, every single project will have a permanent map set. And so that's a great place to store data that you don't want to modify all the time, but you always want to have access to. And then you can organize your project into different map sets. So in this particular example, we have the permanent map set, which has all our reference data that we downloaded. And then we sort of have like 2, I guess, scratch map sets for part 1 and part 2, where we're going to write data to. I don't know if that, yeah, it's a kind of arbitrary way of organizing data, and you can access layers in different map sets.
Well, data set can do multiple map sets or just one?
It can be just in one. That's good. Yeah, so it has to, you can only access things that are in the same like project. But then things that you organize the data within the project into map sets, but you can access data in different map sets. Yeah.
But then the permanent map set is read-only, so it's like shared.
It's not read-only, you can write to it. Yeah, we could have started this session, or we could switch to the permanent map set. And then we'd be writing to it.
So it's like folders?
Yeah, it's exactly like folders in a project. Exactly. That's
So
a good way of using
so
that.
the
Yeah,
reason
thank you.
for that is like they share the projection system in the one map set. That's the point I created the map set.
Yeah, the point of creating the project is to make sure that everything has the same projection.
Okay.
So if you wanted to add any data to this project, it would reproject it when it imported it. Yeah, and then once it's in the project, it can be in any map set, and it has the same projection, and you can access. It's more just for organizing data. Yeah. I know this is the most confusing part of graphs when you first learn.
Yeah.
Which is why we tried to just roll over it. Yeah. Say,
We initialize this whole system with this command DJ.
Yeah. Yeah.
And then it automatically created the map set we run.
this was all already created in the download.
Okay.
Yeah. So, oh, I'm gonna get sidetracked. Okay. What's it? Okay, I'm not gonna get sidetracked. I'm retracting that. We downloaded a folder and it was a GRASS data set. It looks like a directory on or a folder on your computer, but it contains like a hierarchical structure of folders that is GRASS's native format. So you don't, yeah, you don't modify it at all. It's like its own little like GRASS native format folder. And it came with a location and a project already set up inside of it. And these map sets, yeah, but you can create them. It's just another command. And I think yeah, I don't think we covered this one. Okay, this is super confusing. I'm totally on board, and this is great.
Nice.
Yeah, okay, yeah. It's not really important to understand like all the different like project and subdirectories, because it's all kind of organized for us. And if you ever start Grass up, it'll kind of drop you into one. And they have like a little, if you're using the graphical user interface, a little wizard to help you like set up a new project. But projects are just, it's all just for organizing data. And every project is defined by a coordinate reference system. Okay. All right, so because we're doing parallel computation, we're obviously going to be interested in timing things. And so there are two ways we can do it. If we're using bash, then we can use the time command. So yeah, that'll give us that. And this gives us 3 numbers, but we're really just interested in the real time. And then the other way we can time things is with Python. Using the magic time it. And then it has these parameters that let you customize the number of loops and repeated runs you want it to do. Okay, so try it yourself. Construct your own time cell. Pick your language, pick your poison.
What I didn't understand first is you use time though, that cell becomes like or the whole input cell other way afterwards, right? Like function did not exist now. Called function.
I thought it did. Yeah, you're right. It is thrown away. Okay. Okay, but if you're making changes to the Grass database inside the cell, then it stays. There we go. Okay. So if we're running Grass tools with Bash and Python, as I mentioned earlier, there are 2 APIs. So if we wanted to like get some information about our digital elevation raster, then we can use Bash with the R. I think I didn't run the first cell, which is probably my problem. You actually have to import libraries if you want to use them. And yeah, this is my bad.
Now, while you're downloading, can I have a question?
Yeah.
So this command r.that info.
Yeah.
That's now a bash command, which it should be in bash. It's a now program. Right?
Mhm. Yeah, so you could run this from the command line and it would print the same output.
But if I use the window, I can also run bash.
Yeah.
I use it.
Yes, this part runs on Windows.
I think in Windows called CMD.
Yeah,
So it's-
yeah, it uses, yeah, it's the same on both platforms, the syntax. Pretty cool. Well. Does anyone else have any questions or? Oh. Yeah, I guess I can just talk about. Yeah, so whether you're using the R or Python API, the syntax is very similar to the command line. You just have these wrapper functions. So grass script is GS, and then we use the run command to run r.info. And it will output the same. So whether you run it here or there, it has the same effect. And because we're using the same project database, whether we run it in Bash or Python, it's modifying the same folder. So we can switch back and forth without and be running in the same grass session. Okay, well, now in my lesson today. How many people are running in Wholetail? Yeah, okay. Should be fine.
What were you back on do?
I was told that if we have like more than 20 people, that we might, and depending on how many like cores we were requesting, we might start to have trouble. But we're still less than 20, so. We should be fine. Okay, yay. All right. Okay. Yeah. So whether we use the Python API or the command line, the output is the same with r.info. Okay. So many tools in Grass. This is the easiest way to run a parallel program if you're using Grass is to use one of the internally parallelized tools in Grass. And there's a whole list of them. And I know that there are people working on it now to parallelize even more. Yeah, we had Aaron Somensen, a Google Summer Code student who has been parallelizing things for us, and Anna's working on some. But there are generally two types of implementation in CrashJS, both doing multi-threading and C tools. Yeah, because threads have low overhead and they can be spawned efficiently, and they're all coded with OpenMP. Yeah, and OpenMP is convenient because if you don't have it installed on your system, Grass will still run. So that's, I think, why they've chosen OpenMP. And the memory is shared using OpenMP, so you do have to be concerned about race conditions. And then we'll also do some of the tools are parallelized with Python, but those are often like ones that are wrapping the other Grass tools in C. Yeah, I thought this was a good example. Like there's our sun computes the solar radiation, and our sun daily runs our sun for multiple days, but in parallel. So it's a Python, it's implemented in Python, but it's running our sun, which is implemented in C. And the parallelization in our sun daily is done with Python. Okay. But regardless of what kind of parallelization is happening inside of the tool, you tell it how many cores to use with the nprox parameter. So here's an example where we're running r.neighbors, that smoothing one that I talked about a couple minutes ago. And we're running it with a window size of 15, and we'll run it first with 1 core and then with 2 cores. You can change the number of cores if you want, especially if you're running on your own machine. Has anyone computed the efficiency? And the speed up? Oh, really? That can't be right.
And number of words.
We can also use the benchmarking library to make a plot like I showed in the first, in the slideshow. So we'll run this with a window of 3 and a window of 15. And then plot. It takes a minute. Has anyone computed the efficiency from the by yourself? And gotten a number besides 0.05. Yeah, I guess I could mention that in this benchmarking library, you can tell it to go from 1 to 4 cores or 1 to 6 cores. Whichever you prefer. Yeah. Cool. So this, just like when the plot that was in the slideshow earlier, is showing that the parallel efficiency is higher when you have a higher window size as you add more cores. Just like it was earlier. And the speed up, that's interesting. Yeah, so I guess as we, yeah, the speed is like a optimal point of efficiency here, because then it starts to take more time. Yeah. And like I mentioned earlier, yeah, it's a rule of thumb that above 0.5 is a good efficiency. So if we were deciding, if we we're going to submit this job to an HPC, I think that, and we were using a 15 pixel window, 3 cores might be a good place to request, because it has the fastest time and the efficiency is still above 0.5. It actually got slower. Yeah, that's possible. I mean, everything. Yeah, I think the last time I ran it, it was too, but yeah. I think if we repeated it more times, it might be different. I also wonder if, because I'm on Wholetail, if we are starting to have a lot of people using it. But I think it's okay. We got some variability. Yeah.
Side these 2 side.
Any questions about parallelized tools and grass?
So every time you send it to HPC, you will run this task, and then you assign it for to HPC.
Yeah, like you would want to run this test a little bit on your machine with a small portion to get an idea of how many cores you want to.
Will it be like different from the small version to the large version?
Yeah. I'm gonna write this question down for Anna. Cause she's the HPC guru, and I'm not sure what her workflow is when she is deciding how many cores to submit from a job. Like, or how she uses the benchmarking library to inform her HPC decisions. That's a great question. Thank you. So, as we talked about earlier, there are like two different strategies you can use to parallelize your work, the data approach and the task approach. And so if you're doing database parallelization, then if you're using Graphs, the easiest way to do that is with the grid module, which will automatically divide up your study area. And yeah, decomposes it into rectangles and then executes a given tool for each tile and then merges the results. So it all kind of happens behind the scenes. That said, it gets kind of inefficient because it is doing all of this like it has all this overhead of merging the results back. So it's most efficient in parallel when it's used for like really computationally intensive tasks. So one of those tasks might be inverse distance weighting interpolation. And so here we are. Like I mentioned earlier, you can really easily reset the resolution or the extent that you want to compute over. So we're modifying that with g.region, so we're using a resolution of 100 meters. And we just run this command, and every cell that we run after this, it will compute at a resolution of 100 meters. So really easy to resample your data. And then we generate 1,000 random samples of, or 10,000 random samples of the digital elevation model. And then we'll run the interpolation over those 1,000 random samples. So it's not a very meaningful computation, but yeah. Here we are running it. And so the overlap parameter of the grid module is telling us how much to overlap the tiles by. And because we're doing an interpolation, it's important to have overlap. But that's where you set it up. Does that make sense? Yeah.
But we do interpolation based on technically weights.
Yeah.
And every grid cell uses all the weights.
It will subset the points into the tiles, which we've sampled. Yes, we have 1,000 points. And we're going to take those 1,000 points and create a surface with them called IDW. And we want there to be overlap in the tiles so that the interpolated surfaces can be merged back together smoothly. Because if we're using just a subset of the points, we'll get like we need to have overlap because you want them to come together smoothly.
But does it also subset the points or only the output grid?
I think it's subsetting the points, but we're going to check with Anna at that. Okay. I mean, it must be subsetting the points, or it's only interpolating over the region that's within the computational extent, which is done by the tiling. So it's subsetting the points. Yes.
So we have to set the size of this grid manually. Yes, there is no optimization mechanism behind which decides how granulated this is.
Mhm.
So in case of optimization of the scores and all the stuff, you have to try different grids as to say where is this biggest addition to running speed.
Yeah. I think you can tell it. Yeah, you can set the height and width of each pixel. But I think that it will pick it for you if you do not.
I think the wide and heights is more for you, how much random you have. If you have the bigger tile,
Mhm.
and you probably like, you have to, you can split it big, and you read the big tile and you do the computation, and computation also, you have your RAM, right? So you have the limit of your computation, so
Yeah,
the reason we set it out is like, if you use all the processor, how many data we can operate in this kind of RAM size. So it's also like,
if you have the same map of data set, and it's still the same. So it doesn't matter how many parts, how many cells you divide it by this grid. Yes, so the amount of memory is more or less the same. Yes, if you divide this cells into different cores. So my question is, the smaller pieces. So it's, for example, 8 cores. Yes, so it's better to have 8, not 9. to be easier to grasp. So it's easier to have a grid which divides the map into 9 parts and send it to 9 cores, or maybe it's more efficient to divide it to, let's say, 16 smaller cells and send it to the same number of cores. So it's something like that. So thinking about such kind of optimization, yes, what is better, or if you apparently it's up to you how to deal with this. Probably no simple optimization method which could work behind the scenes and calculate this for you.
I'm not sure, but that's a great question for Anna that I've written down.
but I think you can divide by how many processors you have, and you have like, okay, ideal is like 16 processor in one time, and next time it's another 16, and for the last receiver, and you have like probably only have 5 tiles left, so you only use 5 processor for the last iteration.
But how would you know if you were submitting it to an HPC? Like, yeah, the optimal.
Optimal, yeah.
Yeah, if it had an infinite number of cores, a bunch of CPUs that it could use, how does it decide?
There's an issue. I remember from yesterday's lecture that in Linux systems you can fork this process, so they share the same memory. So it is not much memory consumed, but on Windows, all the processes just have their own copy of data. Yes, so in that case, difference between more or less is how it's organized the whole data set. So it's aware of it, probably check how it works. But apparently it is on Linux system, so maybe it's not an issue.
Yeah.
Sorry, does this work well even if I try to parallelize an algorithm that needs a gradient to execute? For example, when I have to delineate a watershed, and watershed are enormous, much larger than the tile you usually subdivide the grid in. So I'm wondering if this approach is good, or it produces when tiles are merged, like spikes.
Like
or
if
something.
you wanted to do like flow accumulation or
exactly,
something, and
exactly.
you wanted to use a database approach,
Mhm.
I just don't think it's well suited.
Yeah.
Yeah, it'd be difficult to do a database approach to it.
So
You need a
just-
more complex approach. Yeah. Although there is some flow modules in graphs that are parallelized internally. I don't know, maybe someone else has a better answer to that.
Oh, yeah, I know because the a parallel interface information. So they would like, yeah, with grids and then from the edge cells, you find out which cells go there.
Mhm.
And then at the end, I think they will also decide on like an order of like the big cells. So you have this, you have the flow accumulation like order thing, and then based on where within a grid which edge goes to which edge, they then decide on all the how do you call this big grid things. They find like an order in that, and then they execute it in that order, and then they parallelize this.
Wow,
Nice.
how does it manage, does it give artifacts? Like I can imagine edges that have flow in multiple directions.
No, because like if this cell is I don't know.
Yeah,
How do you do that?
while you look it up, I'll start this tool. It's the same, but run in serial. So no grid module. Yeah, I know there's one of the graph modules that I have used a lot, RSim water, which does like the St. Bennett equations of overland flow, like Quaternion overland flow. It's parallelized internally, and I've always wondered how it does that, because it's, yeah, there's time steps and it's like doing like some sort of particle tracing. Yeah. Okay. Useful if you time this. Okay. And if you're going with a database approach and like you're tiling, there are some tools that are already like specifically tiled, like our MapCalc for raster algebra. But it's not super efficient. Okay, yes, so here we can see that when we use the tiling approach, it was like 9 seconds, but this took almost 30 seconds to run if we'd done it serially. Did anyone compute the speed up? I can't think on my feet, so I'll try and type that. Three. Okay. So if that was all about tiling data, and how you make tiles in Grass or use its tools that already have tiling built in, the next part is about task-based parallelization. So running different tasks at the same time. And for that, we can use Python or Bash. And so there'll be 2 seconds in here. The first on Python, where we're going to do a multiprocessing example. And so this is where we'll do that view shed example from earlier, where we want to compute multiple different view sheds at different points. And one caveat to this workflow is that when you're using Jupyter or the interactive interpreter, it can't run the multiprocessing library of Python. So we first will write this cell to a file and then execute the file. So the write file magic will take the contents of this cell and put it in a file called example.py. So we run it, example.py. And then here it is over here, the contents of that cell. And then here we are adjusting the computational extent to the digital elevation raster. And from that raster, it will also take the resolution. So we had downsampled to 100 meters, but now we're going to use the resolution of the raster. It'll match it exactly, the extent and resolution. And I think the DEM is a 30-meter DEM. On that. So here we are. We have first create a function that runs r.viewshed. That's Grass's viewshed module. And it takes coordinates as inputs. And it's going to write a raster called viewshed cat. Okay, and we're going to run it for each of the 4 viewpoints that we have there, those coordinates. And with tool processing equals 2, I think we're going to use 2 different threads, 2 different CPD. Yeah. Thank you. Oh, yeah. All right. Fired. All right. So when we call example.py, it goes to if name equals main. It takes these 4 different viewpoints, and with 2 different cores, it maps each of those points onto the viewshed function and executes the viewshed. So there we have computed viewsheds 1 through 4. Okay, but we can also do this with bash. And the simplest case would be just to execute them in parallel in the background. And we do that by appending the ampersand. The wait command forces the script to stop until all the background tasks have finished. So that could be important, like if your workflow you're going to parallelize multiple parts of it, but you need the first part to run before the second part needs to run, then you need a wait command in between the 2. So in this example, well, we're changing the resolution back to 100, and then we're computing the kernel density with a kernel of 10,000 and then 15,000. And then, a wait command at the end so that it will wait until the background processes are finished before doing anything else. And so that's the simplest way to parallelize something if you're using bash. If you have a larger number of tasks, then you might want to use GNU parallel and XRs. And so that's this next example. So this is the same grass command. We're doing kernel density, but this time we're going to do 5,000, 10,000, and 15,000. And we're writing a bash script called commands. And we can open that up. And once we run that cell and see what's inside commands.sh. Oh, it's actually right. So it was for loop kind of in bash. Do each of these lines with each of the R values and write it to commands.sh. And then this part is the GNU parallel part. So here are all 3 of those commands. So each of the kernel density computations commands. And then we're going to time how long it takes to do this parallel computation. Parallel is the green parallel part. And then we're going to use two processors. And we're submitting a job called commands. Oh, okay. I'm going to run this again and then show, yeah, while we're waiting for that to run, you can also open up the terminal and run htop. And you can see, you could see it running. Any questions on that part? I'll use the parallel. All right, so I've been talking so far about how we've been kind of walking around this computational region. And if you are wanting to run over a smaller area, for example, like you want to run like 1,000 different view sheds, but you know that they're not going to be able to see across the entire raster, you might want to just use a small subsection of your region. Just a small subsection that's around each viewshed point, for example. And so you can do that with grass and then run all those viewsheds in parallel. So that could be an example. Let's say you wanted to compute cell phone coverage for all of Poland. You don't want to run a viewshed of the entire country for every single point. There'd be so much redundant computation there. So with grass, you can set it to just run on a small area around each area. But we do that by modifying the computation, the computational region in the environment. Because if you use g.region like we were before, then it will change it for all your different viewsheds that are running in parallel, right? You'll end up with a lot of conflicts, but you can modify it safely using this. Yes, so we've modified the previous example to run parallel viewsheds to different extents. And we're doing it by modifying we're copying the environment and then modifying the grass region inside the copied environment to just have a max distance away from the point that our viewshed is at. So now it's just doing a little square that is max distance times 2 in width and height around each of our viewpoints. And by copying the environment and modifying the region, we're safely doing it so that we don't end up with race conditions. Yeah, race conditions. Let's run that. And again. Any questions on why we did that way, or the advantage of having a computational region? Okay, this is just a note at the end that I'm going to skip because I think we can use the last 18 minutes to each work on this little example, and then we're at the end of notebook 1, and then we can go have some coffee, went to the bathroom, discuss, ask questions. Okay, so here's some documentation from the our Sun module, which is parallelized internally. it has this unprox thing, and it computes solar radiance and radiation, and you can click on the module, the tool manual page, and see all the different yeah, lots of information about it. And I think you can cite it. It has a bunch of yeah, you can cite it, and it's been used in papers, so it's a pretty complex algorithm. Okay, and we're gonna compute the solar radiation for the winter and summer solstices, so that's day 355 and 172 respectively, the spring equinox, day 80, and then your birthday. So you have 4 days that you want to run our sun on, and we want to parallelize the workflow. And so we've learned a lot of different strategies today, and it's quite open-ended. I'll leave it to you to work on it for 10 minutes if you want, and then we can talk about it.
Good.
Yeah, okay, all right. And you can ask questions too, if you want. On my head. It looks like Anna is in the Zoom room. So maybe she'll come say hi. We take a couple more minutes. Too fast? Okay, does anyone want to share what they have tried successfully or unsuccessfully? Yeah,
I'm still doing it, but I thought because you can both decide on the number of processes within the algorithm and then parallelize the three different ones. So now I'm just timing how many processes is fastest for within the roster for a single job.
nice.
And now decide on that and we're gonna run out of them in parallel.
Oh, okay, okay, yeah. I like it. Yeah. The I guess I could have mentioned with you are the slope and aspect is the same for all the days, so it only needs to be run once. Okay, yeah. Oh yeah, okay, all 3 days of the year that you're okay. I thought you meant all 3 of them. Okay. Okay, nice. Okay, cool. So are you using the benchmarking library?
No, I'm just running
Just
time
timing.
in the program.
Okay, cool, cool. Anyone else? Yeah,
I'm still doing it,
Uh-huh.
it's not finished, but I saw something. On top of the note I'm using Cora, it says using to Artisan daily and already run Artisan in parallel for different days.
Mhm.
I think that might be the solution.
Okay, yeah. Mhm. Did anyone decide to try tiling? No. Or well, then if you want to keep on working on it over the break, you're welcome to, but I think we're close enough to the break that I'll say my last bit before we go to the break, which is that if you aren't coming back in the second half, please take a sticker. They're up here. And if you are interested in getting involved more with grass, there's these student grants that you get mentoring and a small stipend for doing them, and I've done one before, and it was great. I like worked, I got paid, and I like picked a small project that I was gonna work on, and I like checked in every week with my mentor and contributed like to Graph's core. And you can find more examples here. I did it over the course of like 3 months, but they used to have like that it was supposed to be 2 months, but that's kind of like the time frame, it's been a couple months, but it can be longer. And then the second way is if you don't want to contribute to like, if you're not interested in contributing to Graph's core, like the projects that they would like people to work on, and you are just looking for help, like how to use Graph in your own work. There's a new mentoring program that we just got funding for from the National Science Foundation in the US. And so if you want to be mentored by someone who's really experienced with graphs, you can get paired with someone, and they get paid for their time. You don't get paid, but they get paid for their time in helping you, so they are like happy to help. Yeah. Okay. Get some coffee.